In this video, we're going to look at how Newton's laws and momentum are related. We're going to get some nice equations from that and use that to explain the concept of impulse. This is Newton's first law. It states that an object will remain at rest, or if it's already moving, keep moving at that constant velocity unless there's a resultant force. So always remember that the first law is all about the resultant force being zero. How does this relate to momentum? Well, if something is moving, it's going to have momentum, and assuming its mass stays the same, then its momentum is going to stay the same. It's really saying that momentum of an object remains the same unless there's a resultant force acting on it. So there's a small link there with momentum. Let's have a look at Newton's second law, which has a lot more to do with momentum. Over here, we can see a definition for Newton's second law. It states that the resultant force of an object is equal to the rate of change of linear momentum of that object. And you need to learn that definition. They do like to ask that in the exam. Some keywords here: resultant force, and the idea that it's equal to the rate of change of linear momentum. Let's write that out. So resultant force, oh, that's a funky pen. Let's go for that one. Resultant force is equal to the rate of change of linear momentum. So P is the symbol for momentum. If we write that as an equation, we've got F equals delta P delta T. Now this is a really useful equation. This tells us that the change of momentum, the rate of change of momentum, which remember rate means per unit time, hence divided by time. And all we've done is we've turned that definition into an equation. So if you learn one, the other one should make sense. This actually comes from the idea that Newton originally introduced that the force is proportional to the rate of change of momentum. And to define the Newton, which is the unit of force, he used this equation and made the constant proportionality 1. You don't need to know that, but that just explains where that equation comes from. Now, this equation is useful in a lot of situations, but a more useful one, and this is when the mass is constant. So it's a special case of this equation. We can derive an equation you'll recognise. So F equals the rate of change of momentum. Now, change in momentum, if we think about it, is just going to be the final momentum, mv, because remember momentum is equal to mass times velocity, minus the initial momentum, mu, u being the initial velocity. Remember that from Suvat. So we've just changed delta P into what it actually is, which is the final momentum minus the initial momentum, and that's divided by time. Now, if the mass is constant, as we've stated up here, so this only applies when the mass is constant, then we can take m outside the brackets, factorise that to get this. You might now recognise this as acceleration. Hello, this is getting good now, because acceleration is the change in velocity divided by the change in time, and v minus u is just the change in velocity. So we end up with this awesome equation, which you already know and have used in GCSE, and this applies when the mass is constant, which is what all the questions you did involved. Some other things to bring out from this equation over here as well. If we take this equation up to here, we just write it slightly differently. We bring the t over to the left-hand side by timesing both sides by delta t. We get this. And this is an important idea in physics called impulse. It has units of Newton seconds. Why? Well, force in newtons, and times it by time in seconds. And it's equal to the change in momentum. It's quite useful when explaining certain things, as we'll see in a minute. And it also helps explain why, for example, we use things like seatbelts and airbags in cars. In a crash in a car, there's going to be a change in momentum because the car's moving and then it comes to a stop and the final velocity is 0. So it's moving with initial velocity of whatever that is, and it has a final velocity of 0. So there's a change in momentum. What we need to do is try and minimise the force on the passenger. We want that as small as possible to avoid injury. How can we do that? Well, we can't really do much about the change of momentum because in a crash, the car's going to have a mass. It's going to change velocities. There's not much we can do about that except make people drive slower. What can we do to the actual design of the car, though? Well, if we look at the equation, the only other thing in the equation that we can change is t, which is the time of collision. Now, if we can make this number as big as possible, this is constant. So if this becomes as big as possible, then that's going to make the force as small as possible because we're timesing these F times t, and we need to keep that number constant because the change of momentum in the crash is going to be constant. So anything that increases the time of collision is going to help. So we want to increase delta t. The way we can do that is things like an airbag. It means you don't stop instantly against the road, you stop in a bag over a slightly longer time, which will reduce the force. Seat belts, they also stretch a bit rather than, again, stopping against the dashboard. The car has a crumple zone. That's the front of the car is designed to deliberately crumple. Here's my awesome diagram of a car. This area here is designed to crumple. Okay, that's why you might wonder when you just tap the car against something, it causes a big dent. Well, it's designed to crumple in, therefore increase the time of collision. If this was made of concrete, no give, your car would stop instantly, delta T would be very small, F would be huge, okay, and therefore you'd be seriously injured. So cars are deliberately designed to crumple. Let's have a look at Newton's third law now and see how that relates to momentum. There's Newton's third law. When two bodies interact, the forces they exert on each other are equal and opposite in direction. Reminder that they act on different objects. It's the same type of force as well. So let's think of an example of the Earth and me, just stood here, somehow hovering in the air, a moment before this experiment starts. At this very moment, the momentum of the whole system here, and this is our system, we have to define the system that we're interested in, is zero, because neither of us are moving. Somehow I'm just floating there, perhaps held up by some sort of magical beast. Then I'm let go. At that moment, well, weight was already acting on me, but let's imagine somehow it wasn't. Somehow weight's just suddenly turned on. So the Earth's going to be pulling me down with weight, and I'm going to apply an equal and opposite force in the other direction, force of gravity on the Earth, which is weight. As you can see, these act on different objects. One's on me, one's on the Earth. The same type, it's a gravitational force. And as we set up here, they're equal and they're opposite direction. Check and check. So it's quite cool, that, isn't it? I'm actually pulling the Earth towards me. But it's so big, remember, it doesn't move, which we talked about previously. So how does Newton's third law relate to momentum? Well, if you think about that, there's a force acting on us, F, is the weight in this case, and it acts on us for an amount of time, however long I'm observing this system for. These two, the force and the time, are going to be the same for the Earth and for me. They're both the same size. The only thing that differs is the direction. And that's equal to, remember, change in momentum. That's the equation we got from Newton's second law. Therefore, the change in momentum for the Earth is going to equal the change in momentum of me. The only thing that's going to be different is the direction. One's going to be positive, one's going to be negative. So positive for the Earth, negative for me. That means upwards is positive, downwards is negative. If we add those two together, since they're going to be equal size but opposite signs, if we add those two together, well, you guessed it, we're going to get zero. And that is really good news because up here, remember we said the momentum before was zero, and we've just proven that the momentum afterwards is also zero. Nice. So just to summarise, hopefully you've seen there how momentum can be related to Newton's laws. Not much to really do with the first law, but kind of relates to that. The main one you need to know is the second law, particularly this equation here and the definition. The third law is also worth applying it to that just so you get a better grip of what that means. Thank you.